This is Mrs. Cribb. I need you to pull out your notes for Chapter 15. We're on Chapter 15.4 for Le Chatelier's principle. And we're going to go along teaching the notes. So when a reversible process is disturbed, it will proceed in the direction that relieves the stress. The stresses include changing the concentration, increasing or decreasing the pressure. Now that only deals with gases. Increasing or decreasing the temperature, and then adding a catalyst. And we're going to go through each one of these things. The first is the effect of concentration. So when you're adding more substance, if I add more SO2 or more O2 or more SO3, it changes the shift of the equilibrium. Now each one of these is really a double arrow situation, so it's going to go both ways. Okay, so I'm going to erase that for a minute because I'm going to write underneath this particular equation, a reaction rather, a lot. Okay, so here, if we're going to add more SO2, okay, here's the SO2. So what you're going to do is you're going to put more of it into the vessel. So here we have a reaction vessel, and inside this reaction container, we're going to have some SO2, and we're going to also have some of the other things. So there, I went ahead and drew them all. Now if I add more SO2, I'm going to put a plus sign right here. So what you're going to do is you're going to put a plus sign under whatever you're adding, and then you're going to point to the opposite direction. So it's going to point to the other side of the reaction. So remember that this is the reactant side and this is the product side. So I'm pointing to the product side. I'm adding more SO2. So that means over here I'm writing more SO2s in here because I'm putting more of it inside my container. What does it do? Well, it shifts the equilibrium from the reactant side to the product side. It shifts from the reactant side right here to the product side. And so that's because I have all these SO2s in here that are available to join up with some of the O2s. This SO2 joins up with the O2 to make more SO3. So these two would disappear. So let me erase that, and we make more SO3. And then these two would disappear again, and we'd make more SO3. So what's happening then? When I add more SO2, what happens to the concentration of the oxygen? Well, since it's joining with the SO2 to make SO3, the concentration of the oxygen went down. What happened to the SO3? Well, since it's shifted from the reactant side to the product side, and I made more SO3s here, the SO3 concentration went up. So by adding this stuff here, the SO2, I'm able to increase the concentration of SO3, but because I have more of this and it uses up more oxygens, it decreases the amount of oxygen inside my container. Now, what if notice I cleaned this up a little bit. What if I decrease the amount of SO2? I take some of it out. So that means over here, I'm going to remove it from the container. Okay, move some of the SO2 out of the container. Well, that means there's less of it to react with the oxygen now. Notice there's not enough of it to react with all the oxygens. So that means when you draw it, you're going to draw the arrow down and then just continuing making the curve. And that means it's going to go from, now it's going to go from the product side to the reactant side. It's going to go from the right to the left. And so when it shifts this way, what's going to happen? Well, if it's shifting from this side to this side, well, that means these things are falling apart into their parts, into their pieces, the reactant pieces. So the SO3s that are sitting over here are now going to fall apart and become O2s. So this SO3 is going to become an O2, and this SO3 is going to become an SO2. And this SO3 that fell apart is going to disappear. It's no longer there. So when I shift from the product side to the reactant side, what happens to the concentrations? When I shift this way, the concentration of the SO3 is going to go down, because you see that this SO3 got used and turned into more oxygens and more SO2s. What happens to the concentration of oxygen? When I shift it from the product side to the reactant side, I increased the number of oxygens I made, so the oxygen concentration went up. All right, now, what if you add more SO3s? All right, now, what if I add more SO3s right here. All right, there's the SO3s. I make my plus sign, and then I point to the opposite direction. Okay, that means in this container I'm going to pour into the container more SO3s. Well, then what happens to the other things in the reaction? If I'm shifting it from this side to the other side, what happens to these other things? Well, now I have more SO3s over here that can fall apart and create more oxygens and more SO2s. So we're going to erase the SO3s and replace them, change this one into an oxygen and an SO2. And when I do that, I got to go up here and I got to erase this SO3 because it disappeared now. So you see that? I lost one of them. Now if I take this SO3 right here and turn it into an oxygen and an SO2. So now we have an O2 and an SO2. And I got to erase this one because it got used up. So what's happening? I'm increasing. The number of oxygens has gone up and the number of SO2s. So when I shifted from the product side to the reactant side, I increase the concentration of the oxygen and I increase the concentration of the SO2s. Now if you decrease the SO3, it does the opposite thing. Okay, so here we have it. I decrease the concentration of the SO3. So now I want to go ahead and just create the curve from one side to the other. That means I'm moving from the left side to the right side now. What happens to the concentrations of these guys then? Since it's moving away to the other side, what happens? Well, since it's moving from the reactant side to the product side, that means I'm using the SO2s and the O2s to recreate the stuff. I'm basically pulling the SO3s out as soon as they're made. So you're taking an O2 and an SO2 and an O2 and an SO2, and I'm using them up over here to create SO3s again. So the O2 and the SO2 concentration inside my container are going down. Both of those are going down because they're being used to create more of the SO3. It's got to fill up that gap. I'm pulling the SO3s out and I'm having to replace them with the ones I just created by joining this right here together. So that creates an SO3 and that creates an SO3. This goes away. So I need a bigger eraser. Okay, but as soon as I create them, I pull them out, and so I have a hole again. So what happens? An SO2 and an O2 form together to fill up that hole. This SO2 and this O2 get together to fill up that hole. Okay, so it's whenever it shifts from one side to the other, it tries to compensate in some way. It fixes it. All right, whenever you change the concentration, it does not mess with the equilibrium constant. And the reason it doesn't mess with the equilibrium constant, remember that the equilibrium constant is the products over the reactants. And really it's, the A times the A, the C and the C on the top and the A on the bottom. But if I add more product, here I added more product, I could add more product. Or there we go. If I add more product over here, remember it shifts it to the opposite side. So even though I'm dumping in some SO3s, that means I'm making this number bigger. What does the equilibrium shift do? It makes this side bigger. So this bottom also goes up. So because I'm changing the concentration, it still doesn't mess with the equilibrium constant because both the numerator and the denominator increase. So the fraction becomes exactly the same as it was before. So now let's move on to the effect of pressure. Remember that only gaseous things are affected by pressure because if you have a container that's 1 liter, let's say this is a 1 liter container. And I'm going to put some gases in there, and I'm going to put 4 moles of gas into this container. All right, so what is the molarity? Remember that molarity is equal to the moles divided by the liters. So if I have 4 moles, I'm going to have 4 moles over 1 liter. That's going to be a 4 molar concentration. That's the concentration of this gas. Now what happens if I squish on it and I push it down? So I have like a plunger here and I push these moles down. and so they have to go, it goes down to here maybe. So I'm going to erase where I had them before, and I'm going to draw the plunger in down to this area, and then those other 2 moles of gas have to still be there because all I did was I pushed them down. All right, now if I only have half a liter, this is now half a liter. Well, I still have 4 moles, and I have 4 moles in 1/2 of a liter, so when I solve that, I end up with it being 8 molar. 8 molar. It's twice as concentrated because I pushed it down. So when I increase the pressure on a gas, it's like increasing the concentration. So if I want the concentration to stay 4 molar, then I need to kind of join these up and make only 2 moles of gases in here. So what I'm really trying to help you see is that it wants to keep the concentration fairly stable. And so when you push on the pressure, when you add pressure to a gaseous reaction, it's always going to move, and it's going to shift towards the side where there are fewer moles of gas. If I release the pressure, see, when I'm pushing on it, I'm shortening the amount of space that's available for the gas to be in. Okay, when I push on it. But if I release the pressure, if I let go of it, it increases the space back to where it was before. All right, here we go. I release the pressure, it goes back to where it was before, so I now can, to have a full 4 molar concentration, I can have 4 moles. So releasing the pressure gives it more volume to work with, so it always shifts the reaction toward the side that has the greater number of moles when I release it, when I decrease the pressure. When I increase the pressure, it goes towards the side that has the fewer number of moles. Okay, we're going to do a couple of examples with this. So here we go. We have this gas. Now remember that the moles are show up as the coefficients. So the coefficients right here, that's a mole. So this has 2 moles of gas, and this is 1 mole of gas, because remember in math you don't have to write the 1, and this is 2 moles of gas. So on the product side, we only have 2 moles of gas. On the reactant side, we have to count all the moles that we have. We have 2 plus 1 to equal 3 moles of gas. So now, if we add pressure, it's going to shift towards the side with smaller numbers of moles of gas because it's running out of room. It's going to shift to make it less concentrated. So it goes from the 3 side to the 2 side. That's a funny looking 2, but from the reactant side to the product side. So when I increase the pressure this time, I'm actually going to create more of the SO3 gas, and I'm going to lose the SO2 gas and the oxygen. Now, if I release the pressure, if I let go of the amount of pressure so the volume goes back up, if I release it so the volume goes back up, well, now it doesn't need to go to the smaller side. If I have more room, it goes back to where I have more moles of gas. So by increasing the pressure, it lowers the amount of space. It goes to the side with fewer moles. If I decrease the pressure, it's going to do the opposite. So in this case, if I decrease the pressure, it's going to shift it from the product side to the reactant side, and that means by decreasing the pressure, I'm going to increase how much SO2 I have, I'm going to increase how much O2, and I'm going to use this SO3 up to make these other 2 guys, because this is going to fall apart. Okay, now let's look at this one. Will the formation of carbon dioxide be helped or hurt by high pressures? So let's look at this. On the reactant side, how many moles of gas do we have? Well, we have 1 mole here and 2 moles there, so 1 plus 2. I have 3 moles of gas on this side. What about on the product side? I have 2 moles. So if I have high pressure, I'm increasing pressure, is it going to help or hurt the formation of carbon dioxide, this stuff right here? Well, it's going to push it this way. So increase in pressure is going to help it this time. All right, what about forming ammonia? All right, and this time on the reactant side, I have 4 moles of gas because there's 1 there and 3 there, and I have 2 moles of gas on the product side. Will increasing the pressure help or hurt? Well, it's going to push it this way, so it's also going to help. So what if I decrease the pressure? If I have lower amount of pressure? If I lower the pressure, it will shift from the 2 to the 4. So that means I'm going to take this stuff and turn it into the other things. It's going to, lowering the pressure would hurt this reaction. I would create less gas. Now we're going to talk about the effect of temperature. We're going to treat temperature as if it's a product or a reactant, like a chemical. We're just going to write it in just like any of the other chemicals. And so when you talk about increasing the temperature, you're talking about increasing the concentration of that chemical. So this right here is an exothermic reaction because the heat is produced. It's on the product side, an exothermic reaction where the reactant side was higher than the product side. The heat went away, so it's produced. Okay? So we're treating that as a chemical. Now, if I were to add heat or increase the temperature, I'd put a plus sign underneath the heat. And then I draw the arrow to the opposite side. So it's going to take everything from the product side over here, and it's going to turn it to the other things. It's going to take this apart and create these guys over here. So by increasing the temperature, I'm going to increase the concentration of SO2, and I'm going to increase the concentration of oxygen, because SO3 is going to fall apart into those pieces. So by increasing the temperature, the SO3 concentration is going to have to go down because I'm increasing the temperature, I'm adding heat. Think of it as the same way as increasing concentration. Well, what if I decrease the temperature? Okay, if I decrease the temperature, that's like taking this heat and removing it from the reaction. So you draw that big curve, and that pushes the reaction from the reactant side to the product side. That means these guys are being used up to create these guys more. So by decreasing the temperature or removing the heat, I'm going to increase, in this case, the amount of SO3 that's being made because it's on the product side. So I'm going to increase the SO3, I'm going to decrease the oxygen, and I'm going to decrease the SO2, the concentrations of them, because these guys, the concentration, the amount of SO2 and the amount of oxygen I have goes down to create more SO3, more of this stuff right here. So by removing the heat, I'm able to create more because this is an exothermic reaction. So let's look at this one. The formation of ammonia is endothermic or exothermic. Well, look at this. The heat's on the product side, so it's exothermic. If it's an endothermic reaction, it has to be written on the other side over here. That's where endothermic reactions are written. And you can write the heat in as the value of kilojoules, like 600 kilojoules were produced. That would give you, that's when you have like a delta H is equal to a negative 600 kilojoules. Negative sign means it's this way. It's exothermic, so you write it on the product side. If your delta H is equals positive 57 kilojoules, you could write instead of heat, you could put 57 kilojoules here. And it's positive, so it's endothermic. It has to be written on the reactant side. So if it's positive, it goes in, and that heat is found inside the molecules. If it's negative, it comes out, and that heat is produced. That heat came from the reactant side. You need to review that, okay? Just stop and rewind and think about it. Okay, so now in this case we have an exothermic reaction, okay, and it asks you, the formation of ammonia is exothermic. Will high temperatures help or hurt the forward reaction? Well, the forward reaction is going from this side to this side. Will it, if I have high temperatures, that's adding heat, that's going to push it to the opposite side, so the forward reaction will be hurt. But the reverse reaction will be helped. So by adding heat, I'm actually going to hurt the amount of ammonia. The amount of ammonia is going to be, the concentration of ammonia is going to go down because ammonia is going to fall apart and make nitrogen and hydrogen. So the concentration of nitrogen and the concentration of hydrogen will go up. So I hope you understand what's happening here. We have ammonia. When I heat it up, this breaks apart into its pieces. It breaks apart and becomes N2 and H2, and the ammonia goes away and is used up. All right, lastly, we're going to talk about the effect of a catalyst. Now remember, a catalyst, it's that bridge that gets you from one side to the other side. And here's the boy, and he wants to go see the girl, and she's on the other side, and the catalyst is right here, is the short way. Instead of him having to walk down and over and up, he can just walk straight across. Gives him another path. So the catalyst allows him to get to the other side faster, but it also allows him to go back faster. So basically it has no effect on the equilibrium concentrations. All it does is just help it to get to that concentration much more quickly. All right, now there's this chart right here that shows you what the effects of all the stressors do. This is the stress column and what happens when you add a catalyst. All right, to add a catalyst, there's no shift. And there's no change in the equilibrium constant. In fact, the only thing that changes the equilibrium constant value are temperature changes. Right here. It's the only thing that affects it. And so you need to really understand this chart. We're going to spend a little bit of time reviewing in class and going over this, but use this chart to help you. And this is where we're going to stop for now. Thanks.